Hi everyone, welcome to another module for Kines 7103, which is taught in Health Kinesiology and Recreation here at the University of Utah. Today we're going to be talking about Chapter 6 from the textbook when we're dealing with models with multiple continuous predictors. In general, what we're talking about in this chapter is shifting from simple regression, where we're predicting one outcome variable as a function of a single predictor variable, to predicting one outcome variable as a function of multiple predictors, or what is referred to as multivariable regression. So multivariable regression is a complicated topic, and it's really foundational for a lot of the other things you're going to go on to do in your statistical design and analysis. And usually, right, it makes sense that conditioning our predictions on a single variable isn't going to be enough. This is because, most of the things that we might be interested in, whether it's, something as seemingly simple as height, something more complicated like academic achievement, or, the probability of winning a match, in a sports setting, these are all caused by multiple factors, or at least, associated with multiple factors. Things don't necessarily need to cause the outcome in order to be related to it. But in any event, we're often going to have something that's a lot more complicated than a simple relationship between a single x variable and a single y variable. If this was the case, if there was only truly one association between y and some other value, any errors in our data would be due to measurement error. This often isn't the case, though, right? We will have y that's related to some x, but it's probably also related to some other x's. And in that situation, the errors that are arising in our data, some of them almost certainly are due to measurement error. But a lot of the times, these errors are actually going to be due to incomplete knowledge. So this is what some people refer to as epistemic variability rather than ontological variability. Ontological variability means that it's some sort of inherent variation and we'll never get exactly the right answer. Epistemic variability means that we have errors, we have variability, but it's due to incomplete information. And if we had all the information, we could make a more accurate or perhaps even a perfect prediction, right? So in most situations, we think that the errors that we observe in our data are a product of both measurement error and variables that we haven't accounted for, right? So we might have measured one x variable, but there are probably several other x variables that are associated with our outcome that we haven't actually measured yet. And furthermore, even if we, do go out and measure these variables, there are still going to be variables that it's unlikely that we've accounted for. Very seldom are we going to have accounted for everything, and that's actually okay, right? There's sort of a strong tendency to want to explain all the variance with the assumption that then you have a perfect model. But actually, a lot of the times the goals with models is to reduce the dimensions of a problem. We don't necessarily need to account for every possible percentage of variance, but we want to have the dominant variables that relate to the outcome. And if we can present a more simplified outcome that explains a lot of the model, we've reduced a very complicated problem down to its most important dimensions. So, in most situations, we're going to have something like this, where we're going to try to account for many of the variables, but some of the variables are going to be unaccounted for. And that's okay. The question will just be, how much unaccounted variation in the dependent variable is left over, and do we still have a lot more work to do from sort of a model building perspective or a scientific research perspective in order to explain variation in the outcome? Further, it's important to clarify that causation is not established by the statistical relationship, but by the logical analysis / experimental design. You've probably often heard the phrase correlation is not causation. I would modify that slightly to say association is not causation, because correlation is more of a specific statistical test. And there are lots of other types of tests we could do to measure associations. So even though they're not correlations in name, there could be other statistical tests that similarly don't get at causation, right? Oftentimes, we are measuring associations with our statistical analysis. In order to get at causation, we have to have a logical analysis that allows us to build something like a causal inference model, or we need an experimental design that allows us to control for some of the confounding factors and really attribute causation to the variable that we're manipulating. And causation is a hard thing to establish. But just to show you that, association is not causation, let's look at some example associations. In the first case, I could have two sort of predictor variables, two x's that both have a contribution to y. Maybe let's say these are two factors that both increase your mortality risk, right? So if the outcome is mortality risk, doing either of these things is bad for you. They both increase your risk, right? And so then as this goes up, y goes up. and as this goes up, y is also going to go up. So this would be a multi-causal situation in which both of these things are associated. However, I could also have a situation in which both x's are associated with y, where it's not multi-causal in that fashion. Maybe x1 causes y, but y then causes x2, right? So this could be a situation where some sort of baseline condition affects your performance, but then how you perform affects your mood, right? So all of these things would be related. As x1 goes up, y goes up. As y goes up, x2 goes up, and therefore these would also probably be related positively. And we would have similar associations to what we had here, but the causal pathway is very different. Or, right, in sort of a third scenario, it could be the case that x1, x2, and y are actually all caused by some underlying third variable, let's call it z. And if z has a positive effect on each of these, right, we'd observe all of these going up together. So all of these values are going to be positively associated, but none of them actually cause each other, right? They're all actually caused by this underlying third variable. So that's one of the important caveats when we talk about multiple regression in this framework, is it's very easy to fall into a trap of interpreting your effects as if they were causal. But regression is just measuring associations. In order for us to interpret cause, we have to have other constraints in the design and the analysis that actually allow us to attribute causation to one of the variables and the impact that it has on the other. So to understand these multivariable relationships, we're going to look at the relationship between students' heights, weights, and ages that was presented in the chapter. These are all things that, intuitively we're somewhat familiar with, that older children are likely to be taller, and taller children are likely going to be heavier, right? So weight, age, and height are all going to be related, and we've plotted that in this sort of three-dimensional grid, doing my best to show you this multi-dimensional relationship here. So weight is plotted on the y-axis, height is plotted on the x-axis, and age is plotted on the z-axis. And so these dots are color-coded based on age, right? So they're red if they are younger, and they fade into black if they are from older students. And then as we look from left to right, we can see students getting taller. So students get taller, right, as we go across the x-axis, and there seems to be a positive relationship with weight here, confirming our suspicions. Also, as students get older, as we go along the z-axis, their weight tends to increase, right? But height and age also go together, and students tend to get taller as they get older. So we have two factors, height and age, that seems to have positive contributions to weight. However, they're both also related to each other. So how can we account for the fact that age and height are related to each other to identify their unique contribution to age? That is, we want to say, all right, given if two students were the same age but different heights, would the taller student still be heavier? Or if two students were the same height but different ages, would the older student still be taller? Right? So when we start adding these multiple components to our model, we have to account for the relationship between our predictor variables in order to say what is the independent contribution of x1 or the independent contribution of x2 to the outcome. So we're going to walk through this in more detail, but broadly speaking, our multivariable model, right, is that we have some outcome variable, y, as a function of an intercept, a slope times our first x variable, and a slope times our second x variable. And as always, right, the intercept is the estimated value of y when all of the x's are 0. This slope is the estimated change in y for a 1 unit change in this x. And this slope is the estimated change in y for a 1 unit change in this x variable. Now, if we actually fit this using the data in the book, you'll find that we get parameter estimates that look like this. Here I've rounded things off to 2 decimal places, but we get an intercept of negative 141.22 plus 3.60 times height plus 1.28 times age. So the estimated weight for a student of 0 height and 0 age, right, is negative 141.22. Not particularly interesting, not very realistic number. However, if we have, for our slope, we have 3.60 times height, right? And this is the estimated increase in weight in pounds for a 1 inch change in height. So as height goes up by an inch, we expect weight to go up by 3.6 pounds. Similarly, as age goes up by a year, we expect weight to go up by 1.28 pounds. The added complication, though, is that these parameter values, right, 3.60 and 1.28, are the effect of height controlling for age, right, and this is the effect of age controlling for height. However, what we haven't really established is what does it mean to control for age when we're interpreting the value of height, and what does it mean to control for height when we interpret the value of age? So in this module, we're going to do that visually and try to show you kind of conceptually what it means to control for one variable over the other. And then in the subsequent model, we'll actually walk through the statistical analysis in R to show you what the multivariable regression is actually doing. So first, we're going to talk about how do we control for shared variance, right? The idea is that age and height are related to each other, so we need to account for that shared variance in our model. So if you think about the variation in each variable, right, we have the variation in weight, the total sums of squared errors in weight could be represented by a circle. Variation in height, the total sums of squared errors in height could be represented by a circle. And we have the total sums of squared errors in age represented by a circle. So these circles represent the total variance in each variable, and areas of overlap represent the shared variance. If I add B and C together, that's what weight and age have in common. If I add A and B together, that is what height and if I add A and B together, that is what height and age have in common. If I add A and D together, that's what weight and height have in common. And if I add C and D together, that's what weight and age have in common. Notice that B is common to all three, and that's going to be important when we talk about how to interpret these effects. So the effect of height controlling for age means that we remove the shared variance from age and height and weight and age to look only at the parts of height and weight that are independent of age. So when we look at height in that multivariable model, we're excluding all of the variation due to age from both height and weight. So we were excluding part B here from the middle, right? And we're excluding that from our height variance. So we're taking the part of height that's unrelated to age, and then we're saying how much of the total height variation co-occurs with the weight variation. And so then this area of overlap is the part of weight that is related to height, but is independent of age. So we're going to use R to show you statistically how this works in more detail, but in simple terms, we can also think of this as the effect of height holding age constant. That is, assuming we had lots of people of exactly the same age, how would we expect their weights to vary as a function of their heights? Right? This is the part of height and weight that's independent of a person's age. Flipping this around, right, we can also look at the shared variance between age and weight, excluding the part of age that's related to height and excluding the part of weight that's related to height. So again, we're excluding that shared variation from the middle in order to say how much variation in weight is now explained by the part of age that is independent of a person's height. So again, now this would be if we're holding height constant, right? How much of an effect does age have for two people of the same height? Note that when we walked through this, the shared variance is completely excluded from both variables, right? Because we want to look at the part of height that's independent of age. So in order to do that, we have to exclude the part of age that's related to height. And over here, we want to look at the part of age that's independent of height, so we had to exclude where height and age overlapped, right? So in both situations, we're removing this variation in the middle from either variable. And sort of conceptually, you could think about this is if I have height and age in the model and I don't exclude this variation, I'd be counting it twice. Because here I have, in this blue circle, the part of height that's related to weight. And then over here in this yellow circle, I'd have the part of age that's related to weight. And if I didn't exclude this common variance, I'd count it once for height and I'd count it once for age. So in order to avoid double counting this shared variance, we exclude it from the very beginning in order to then look at the part of height that's related to weight independent of age. So, you can think about that as we're cutting out this little part of the circle to then look at how much variation is in this shaded area here where the two overlap. And similarly for age, right, we're cutting out this part of the yellow circle in order to look at how much variation in weight is explained in this part of the shaded figure. So we need to exclude that common variance, and this can lead to a problem if both variables are highly related. So if they're in the first example, there was some shared variance, right, but it wasn't huge. But now we're going to talk about an example where we have a massive amount of shared variance to try and illustrate why this might be a problem. So this is what's referred to as collinearity between our variables. If both of our predictor variables are highly correlated, they are what we would call collinear. So collinearity is an issue when we have two variables that are highly correlated and we're trying to predict a third. So for instance, if we're trying to predict total height as a function of left leg length, on its own, left leg length is probably a very good predictor of a person's total height. Taller people are going to have a longer left leg. There's a lot of shared variance between those two variables. However, if I put both left leg length and right leg length into the same model, their shared variance now has to be excluded, right, for the reasons that we talked about before. So this area where all three circles overlap is getting taken out of the model because we can't double count it for both left leg length and right leg length. And if we're controlling for that correlation, right, people with long left legs also tend to have longer right legs, and we exclude that variance, we're going to run into an issue because now once we've excluded that, we're looking at the part of left leg length that's unrelated to right leg length. So that's a very narrow sliver right up here. And we're looking at the part of right leg length that's unrelated to left leg length. And that's this sliver over here. So even though left leg length is related to height and right leg length is related to height, if I put them both in the same model, chances are we'd see that neither one is related to height. And the reason for that is controlling for right leg length, left leg length doesn't explain a lot of variability. And controlling for left leg length, right leg length doesn't explain a lot of variability. These are collinear predictors. They have a really big correlation between them, so when we exclude their shared variance, we essentially ruin their predictive value because it's actually the shared variance that relates to total height. So when we have two variables that are highly correlated, we have to think carefully about should we put them in the same model. And usually the answer is no, we shouldn't be putting them in the same model. We should be doing something else in order to accommodate that correlation. If one of them is a better measure, maybe we just put that one in the model. If they're related measures, there are ways you could average them together or more sophisticated and I would argue more appropriate ways to create a new variable that would allow you to say, okay, well, let's just put this shared variance in the model and see how that shared variance relates to total height. Now, hopefully this sort of visual demonstration helps you conceptually understand what's going on in multiple regression. In the next module, we'll be walking through step by step how we actually do this math to calculate these parameter estimates using R.